So my name's Duncan Quincy. I'm at the University of Leeds and I'm a remote sensing glaciologist. And that was my role in this project, in addition to, I suppose, conceiving the idea with Anne and Bryn, and then running with it till we got to the point where we could actually get onto the debris-covered tongue of Khumbu and start to drill in some anger, actually, literally at times, of course. So, I mean, first of all, thanks very much to Tavi and to the IGS for giving us the opportunity to talk about our project. I should acknowledge that we were funded by NERC, and this was a joint venture between the universities of Leeds, Aberystwyth and Sheffield. And we also worked very closely with Kathmandu University and also with Kircher, the pressure washer company, the reasons for which should become apparent later on in the presentation. So I've got next slide, Katie, but I guess it's Bryn. Next slide, please, Bryn. Excellent. So we've got a long list of other collaborators who really helped us out a lot on this project. I would like to give special mention to Himalayan Research Expeditions, who provided us with some amazing logistics over 4 field seasons up at very high altitude. Also Mahesh Magar, who was our guide and who kept us safe during that time, and particularly also to Tenzing and to Dawa Sherpas, who provided scientific expertise, but also actually literally took us into their homes and looked after us while we were on site. Next slide, please, Bryn. So we are going to be talking about the Everdrill project. We focused on the Khumbu Glacier, which you can see there in the image. This is what could feasibly be called the world's highest glacier, as Tavi mentioned. It flows from the flanks of Mount Everest through a dramatic icefall, which is the Khumbu icefall, which people may or may not be familiar with in terms of climbing routes up Mount Everest, and down through into this long debris-covered tongue, which terminates at around 5,000 meters above sea level. And as you can see, it's very heavily debris covered. So we, in a nutshell, aim to penetrate through this debris and into the interior to explore some of the internal characteristics. Next slide, please, Bryn. The Himalayas are the largest glaciarized area outside the poles, and surprisingly, perhaps until about 15 years ago, was very poorly studied in comparison to some other glaciarized regions. But since then, studies have really accelerated in number very rapidly as the links between glacier behavior and the local people have really become more realized. And so studies on ice dynamics and glacier mass balance and surface characteristics have become very prevalent in the literature. And I think some of the most recent work here on the left by Fanny Brun and on the right by Amari De Heck have really linked the very negative mass balances that we see over in the eastern part of the range with deceleration or even stagnation of the ice tongues as that ice flux has diminished or even ceased in parts. And more up to date again, looking at some of Romain Hugonet's work very recently, he really spelled out very clearly how important the Himalaya is in terms of global glacier mass loss, and also how important it is in terms of the increased rate of mass loss that we've seen in recent years. Next slide, Bryn. I think what makes the Himalaya particularly special is because of that clear link between the glaciers, the meltwater that comes off of those glaciers, and the people who live in the foothills and further downstream. You can see some of those images on the right. There's an image at the top of a chap in the Karakoram literally harvesting the water from the glacier tongue to take down to the village for drinking and for sanitation purposes. The middle image is some folks in Nepal using the meltwater for washing and for sanitation purposes. And then at the lower right, there's a hydropower plant which has been installed in the Langtang, which is becoming increasingly the case in the high Himalaya, using these glacial systems as potential water resources to generate power. And on the left-hand side, you can see an example of a very broad regional study from Arthur Lutz, which demonstrates that for each of these major glaciarized basins, the glacier meltwater input into the hydrology is perhaps less than some of the other components, but still quite significant, and has been over the reference period of this study, which was in the early 2000s, and is projected to be forwards for their future projected period, which was 2041 to 2050. And perhaps what we don't see from this study is the important role that the glacier meltwater plays in times of potential drought. So any change in the regional picture of these glaciers has a real knock-on effect for the people living in the region. Next slide, Bryn. So while we've got a good picture of what's going on at a broad regional scale, I think perhaps where we don't do so well is really being able to project forward what's going to happen on an individual glacier basis, or perhaps within a catchment. And here you can see on the left-hand side a series of studies that all had the same aim, which was to project volumetric loss in the Everest region until the year 2100. And you can see the broad range of projections we've got, going from 8 to 10% volumetric loss by 2100, our own work at the bottom of the slide, all the way through to, in the worst case scenario, 99% with some of Joe Shea's work. And so what we sought to do was really get to grips with some of the parameterizations of the modeling that goes into this sort of work. And the only work that we had to go on previously was some ice temperatures from the 1970s, some work by May et al., who concluded that the Khumbu Glacier had a surface layer which was generally cold, but beneath that, some warm ice at depth. And then on the northern part of the range, some work by Liu et al. Concluded that the glaciers were cold. So how then to parameterize these models? It's extremely tricky. And so we sought to get into the interior to really collect some of these internal characteristics. And that was the aim of the Everdrill project. Next slide, Bryn.
Thank you. Well, that's me. I'll take over on the logistics and the drilling component of the talk tonight. So there are basically two main considerations to getting there. And so usually when we talk about field projects, it's how do you get the equipment there and to perform. But in this case, rather uniquely, we have to get ourselves there as well, because the field site on Khumbu is about 5,000 meters above sea level. So I'll talk about these for a couple of minutes. It's the Everest Base Camp trek to get there, which is an extremely well-populated route up the valley from Lukla to Khumbu. Everest Base Camp is on the Khumbu Glacier. And here we see some of the equipment going up. The porters are rather merrily carrying up packs of 30 kilograms plus here. The cows help out, and then while I am puffing my way up, puffing and panting, carrying 7 or 8 kilos. So quite a lot of the small equipment can go up, hauled up the tracks. And as I said, it is the base camp trek. And that's for acclimatization purposes as well, requires 6 or 7 days to get up from Lukla, the nearest airport, to the glacier. So here we are below the tree line, extending up above Namche Bazaar here, some town villages on the route up this famous trek, and acclimatizing until we go here, until we get above the tree line. And on the left, you can see a heavily debris covered glacier coming down with its latero-terminal moraine, which is actually pretty indistinct from the glacier surface itself in this case. So for those people who are seeing these for the first time, that is not a rock glacier on the left-hand side there. There's a debris-covered glacier coming down the valley and flowing within its own bounds. The Khumbu Glacier has it flows off Mount Everest, so that's the claim for it being the highest glacier in the world. It's got the highest accumulation area up on Everest, down into the western Khum, flows down the Khumbu icefall, past base camp, and then along this heavily debris covered and low angle glacier tongue, which extends for about 10 kilometers. And most of our work was on this tongue here, as I say, about 5,000 meters above sea level. This is what it looks like on the ground. So this is, you could be forgiven for thinking this could be down glacier, looking at the glacier itself and not the head wall behind, but this is up glacier. So it's extremely low angle, the debris covered tongue is effectively because of the insulation afforded by the thick debris layer on the surface. And immediately, if one saw this, if I saw this 6 or 7 years ago and I was asked to be drilling a hot water borehole on here, I'd be thinking twice about it. Nonetheless, you'll see that there are possibilities and locations for doing this, and we did manage to do so. Meanwhile, we've got ourselves there over 7 or 8 days. Quite a lot of the small equipment has got there, but we can't break everything down to the size that can be carried by a cow or a yak. And so here, some of the equipment comes up by helicopter. One of the reasons for choosing Khumbu was that it is the route for attempts to the most popular way of route up Everest. And therefore there is a lot of helicopter support logistically in the valley. And here's a helicopter with a net slung underneath. But another consideration here is that the low pressure of the air and the low oxygen content at altitude, the low density and oxygen content at altitude. And so this helicopter, which would have a payload of in excess of a ton at sea level, our limit was 175 kilos each load. So even then, the whole operation needs to be scaled down as much as possible in order to carry it out on the glacier. So you can get the equipment there, and we can get ourselves there, but then there are a few other logistical considerations as well. And some of these we really couldn't answer until we actually got on the ground and on the glacier. And these are listed on the left here. In terms of the oxygen supply I've mentioned, it severely restricts human activity, but it also severely restricts the activity of the effectiveness of combustion motors, and indeed whether we could even get combustion motors to start at that altitude. Another consideration is the surface debris and finding our way to the surface ice in order to drill these boreholes by using hot water. And then even if you can start, then there's end glacial debris to be overcome. And this was unknown pretty much. So this really was an unknown. We could have begun this project and just repeatedly hit debris, and it frankly, it wouldn't have surprised me that much. That would have been it really. But we'll be able to talk a little bit more about that, and Katie will give some results. Basically, it wasn't as debris laden as one might have thought, looking at the image like this on the right-hand side. And then more in terms of, I mean, we need to be safe while we're drilling, of course, and the team needs to be safe. So you can't be under some of these rather loose boulders on a melting surface. But there's also the data loggers to be left behind and experiments left in place. And so one has to consider the stability of the site through the subsequent wet season, because we need to reaccess that instrumentation. So here you see Khumbu marked by a yellow star, and across the x-axis is elevation, and the y-axis is the power output relative to sea level. So you'll see in terms of the power output decreasing with elevation that we're down somewhere just under 60% of the power output from this equipment. That means the hot water isn't going to get as hot, and the pressurized water isn't going to be as high pressure, if we could get it going at all, because we're actually off the top of the scale for adapting the carburetor jets as well here. You have to adjust the fuel flow into the carburetor to match the oxygen. And so in order to overcome that, we worked with Glacier, who produce commercial car washes, and they did some wizardry on the carburetor on the motor, and also ruggedized the units. And you'll see here that we are actually drilling. This is a high pressure hose moving, and it's going over somebody's shoulder here down into the borehole. So we did actually get them going. It took a little bit of coaxing, I must admit, but the motors do work there. I think we were right at the limit, the altitudinal limit at which they would work, because they would vary, their performance would vary with air pressure, varying with weather conditions. And also if one just moved one's hand over the air intake to the high pressure pump on the left here, it would start to cough and splutter and think about stalling. It was that sensitive at the elevation we were at. The overall setup is illustrated here. On the left-hand side is a photograph of the drill site with most of the main components. And on the right-hand side, a conceptual sketch of those components in place as they are on the left. So we have to find a superglacial pond or a water source at least. Then the water is pumped out of there under low pressure to a settling well or a stilling tank, which we use an IBC tank here holding 1,000 litres roughly. That then feeds a low pressure hose to the high pressure pump. The high pressure pump feeds through a high pressure hose through the burner. So the burner unit then is heating up the pressurized water. And the pressurized water, the hot pressurized water then extends through the spool on which we have about 175 meters of hose, of high pressure hose. And then it's extending over a tripod and the sheave wheel and down the borehole. And here's the borehole in the image on the left-hand side. So that's the setup, and I'm pleased to report it did work. In fact, it worked rather well on Khumbu Glacier. Yes, we lost power. Yes, it was slow, but a lot of the glacier conditions played in our favour. So you'll see here, even on the ice cliff exposed by the undercutting of this pond, there aren't masses of large debris layers protruding from that, so it gave us hope. We also had to consider end glacial debris and as I said, the wet season stability. So in terms of end glacial debris, before going, we had no idea, as I said, but here's the top of one borehole with the water coming, we're drilling actively here, so the water's coming back up the borehole and out through the overflow stream at the surface. This is about 12 to 15 centimeters diameter, but you can see very fine particles here in the ice. So this is fine dust embedded within the ice near the surface. That's no problem immediately to prevent it in terms of preventing the progression of the hot water jet down the borehole. But here lower down, we're hitting at a depth of some tens of centimeters here just below the surface, a couple of much larger clasts protruding into the wall of the borehole. And in this case, they didn't stop us drilling. In several boreholes, we were stopped by hitting an end glacial layer. We think it was just one. But what can happen when you have a situation like this is there's a gradual buildup of debris down at the base of the borehole, because obviously if you melt the borehole larger, this clast here, for example, at about 5 o'clock, will fall out down into the borehole and they accumulate at the base, and the water jet then is no longer really effective at transferring the heat and mechanical power to the melting face, and you just progressively slow down and slow down. And there's another indication of that. This is the high pressure, this is the very small diameter nozzle, whole nozzle that we use for the drilling, and the nozzle adapter. On the left-hand side, from a normal borehole or pre-drilling effectively here on Khumbu, and on the right-hand side after just one borehole down at site 1. So you can see the wear on these adapters down to the brass and around the edge. So it's clear that there is debris within the boreholes, but it didn't stop us drilling in many instances. As I say, that was quite successful. So we managed over the 2 seasons of drilling to drill 27 boreholes. 2 of those were longer than 500, were greater than 150 meters in length, and that's limited effectively by our hose rather than being prevented by the glacier. These were carried out at 4 main sites, 1, 2, 3, and 4, which I'll come on to in a second. And at each of those, we carried out several experiments, but the most successful of which, and the ones that Katie will talk about in a couple of minutes, is the Optical Televiewer logging of those boreholes and the installation and recording automatically of thermistor strings in them to determine end glacial temperature. So this is the Optical Televiewer about to go down a borehole. It provides its own light source and records a complete image of the borehole wall as it's lowered or retrieved. Katie will talk about that a little bit more. And here's a very ruggedized version of a thermistor on highly ruggedized cable ready to go down a borehole. And then that will be recording through time at a fixed point along the end glacial vertical transect. So this is the summary of the sites and the boreholes. I'll draw your attention for the moment just to the central panel. This is the Khumbu Icefall, Everest Base Camp, and we have 4 sites really that I want to draw your attention to for the rest of the talk. Site 1 is near the Glacier terminus, in between some lakes. But it was in between some lakes when we drilled it. It actually became a lake after a little while. More on that later, or perhaps offline. Sites 2 and 4 are in the center of the tongue, 2 on the west and 4 on the east, and then site 3 just below the clean ice and the ogives ice here, below base camp, so at the upper part of the tongue, when you're getting to the base of the influence of the icefall. So 1 at the terminus, 2 and 4 in the middle, and 3 up towards the top. And then the panels around the outside of the central one are showing the numbers of boreholes at each site and which one was instrumented. So we're drilling multiple boreholes at each of these sites. I'll hand over now to Katie.
Thanks, Bryn. So just as a brief introduction, I'm Katie Miles. I was part of the Everdrill project for my PhD research. At the moment, I'm lecturing at Aberystwyth, but come January, I'm going to start a postdoc with Bryn. And I'd like to take you through 2 different types of the results that we collected from the Everdrill project. First, I'm going to talk about the ice temperature measurements, and then, as Bryn said, the optical televiewer results, and in particular, the young glacial debris content that we picked out from those images. So the temperature measurements were made with thermistor strings, as Bryn showed in one of his last slides. These are strings of thermistors so that we could measure the temperature at various depths through each borehole. We had a number of different lengths of strings in each of our boreholes, according to how deep the borehole was. So our longest borehole for the thermistors was site 3, and we had a deepest thermistor at 130 meters. 3 of the sites, 1, 2, and 3, were deeper ice temperatures, and the 4th site was a shallow ice string, so we only put thermistors into 7 meters. And the measurement periods for each of those sites vary according to when we drilled the borehole and put the sensors in, and also to how soon the cable snapped. So to jump straight into the results then, this is a time series of some of our thermistor data from site 3. The stars indicate data points and the dots indicate data gaps from cable snapping. So we're thankfully, due to revisits, we're able to rewire the thermistors back in to the logger and keep collecting data. The thermistors are color coded by depth. So we've got gold towards the surface and a darker blue at depth. And the naming convention for the thermistors is the site followed by the depth beneath the surface. So S3 refers to site 3 and 4.7 to 4.7 meters depth below the surface when we installed the thermistor. And what we can see from this time series right at the start is the freezing curve in. So when we drill the boreholes, as Bryn said, with hot water, there's water sitting in the borehole when we lower these thermistors in. But over time, that water freezes. And we see this freezing curve then as the thermistors within that water freeze in and settle to the temperature of the surrounding ice. And beyond that freezing curve, we can see that actually the temperatures are generally very stable over time. And from these stable temperatures, we were able to calculate what we refer to as the settled ice temperature. So the second plot is color-coded in the same way as the first. We've got gold-colored circles for the thermistors closer to the surface. And this is a plot with depth, so the darker blue is the deepest thermistor. And these settled ice temperatures for the thermistors that froze in, we calculated from a short-term average of the temperature data far into the record where we knew the thermistor temperature was stable. Other things to point out in this plot is that the grey band near the top indicates the seasonally influenced top layers of ice. So those that will react to changes in the air temperature. More on that in the next slide. And the dashed line down the side indicates the melting point temperature for each of those depths. And we can see from this that with depth, the settled ice temperatures of these thermistors increases almost linearly with depth. It's quite a nice plot. So this is for our site 3, as I said. We also did these plots and this analysis for our other 2 sites. At site 1, none of the thermistors froze in. This is because we only got 3 weeks of measurements. And as Bryn alluded to, this is because we had to rescue the logger and cut our loggers because the ponds either side of where we drilled the borehole started to expand. Only one of those thermistors began to freeze in. And from the start of that freezing curve, we could extrapolate and calculate, estimate what we thought the settled ice temperature might be. The rest of them, we simply had to assume the ice was warmer than that of the uppermost thermistor. At site 2, all the thermistors froze in, and they also show a very similar trend, linear increase with depth to the site 3 profile I've shown here. Just to jump to site 4 briefly, this is the shallow string that I mentioned we had. Again, another time series of data with the same color coding convention and naming conventions. We've got a gold colored line for the thermistor nearest the surface and dark blue for that at 7 meters depth, because this was our shallow string. And again, we can see the freezing in curve of these thermistors. They all froze in. That was in June 2018, about a month after we installed them, just after that little data gap that you can see. But where this plot gets really interesting is later into the record, around November, where we can see what is ultimately the propagation of the cold wave change in air temperature through these layers of ice. So the change begins in the upper ice layers, and you can see the biggest magnitude changes with that uppermost thermistor at 1.5 meters depth. And that propagates through, it's delayed, and the magnitude of the change is subdued with depth, and ultimately gets through to the deepest thermistor at 7 meters. Unfortunately, we didn't have simultaneous air temperature measurements to do anything nicer with this, but it is quite a pretty plot, I think, that does show the propagation of that cold wave at depth. So to jump back to the deeper ice temperatures then, I just want to put this in perspective for the whole glacier. So this plot shows those settled ice temperatures that I showed a few slides back for each borehole at the relevant depth of that thermistor. We've got colder temperatures shown in bluer colours and warmer temperatures in yellow to red. We can also see on here what we call the CTS, the cold temperate transition surface. And that's where we've got a switch from cold ice to temperate ice, or ice that is at the pressure melting point. I think what we can see from this plot, first off, is that we've got a polythermal glacier. We've got colder ice, upper glacier towards the left in the upper ablation area, and warmer ice, particularly at depth, towards the terminus, up towards the surface as we get to site 1 potentially. Another important point is that the coldest ice that we measured was only minus 3.3 degrees. In the grand scheme of things, this is nowhere near as cold perhaps as we expected coming out of the western comb of Mount Everest, and also not very cold compared to measurements elsewhere. For example, in Greenland or Antarctica, you might be looking at minus 20, minus 40 degrees C. So that's fun in itself. Also on this plot, we can see the mean annual air temperatures plotted for each elevation, or approximately for each borehole elevation. If we compare those to the ice temperatures in the borehole, we can see that the ice is up to 2 degrees warmer than the mean annual air temperature for the relative elevation of each borehole. And this means that there must be extra heat coming from somewhere, and we don't really know where this is coming from or why. Perhaps it might be some heat within the glacier, something to do with latent heat. Or perhaps it might be effects of climate change being felt deeper in the glacier than perhaps we might have thought beforehand. The other thing is that we had one historical measurement with which we could compare our results to. There was a measurement made in 1974 by Mai et al. The location shown by the cross in the figure, so about a kilometre up glacier of our site 3. And they measured a temperature of minus 5.3 degrees C at 2.7 meters depth. Now, hopefully you'll notice that that's within the seasonally influenced upper layers of the glacier. So when we picked a measurement to try and compare to this, to make it as comparable as possible, because we've got a couple of issues in doing this comparison. We picked our thermistor that was closest, so the closest borehole was site 3, and we picked our shallowest thermistor, so 4.7 meters, not quite the same, but still well within the upper limits of that seasonally influenced layer. And because it's in the seasonally influenced layer, we wanted to pick a time of year that was as comparable as possible to their measurement, which they made in November. And at the time of doing this analysis, the latest we had was October. And the temperature that our thermistor measured at that time was minus 2.3 degrees. So that could suggest that the ice has warmed by 2 to 3 degrees in the 43 years between these measurements. And this, of course, has implications for future projections of glacier melt, and one of the next steps for the Everdrill project that Anne might be talking about is that we're going to implement these temperature measurements in models forecasting how long Khumbu Glacier might survive. So moving on from the ice temperature then to the optical televiewer logging. Just a bit of background to optical televiewers. Bryn covered a little bit. They're cameras that take a 360-degree image of the borehole wall. They're orientated through a magnet in the tripod that's used to lower the optical televiewer down the borehole, and they provide true color, geometrically accurate and high resolution images. So we're getting less than a millimeter vertical and horizontal resolution. And the vertical resolution is controlled by the rate at which we lower the televiewer, and we log at a speed of about 1 meter a minute. And the horizontal resolution is controlled by a number of pixels that the camera views on each rotation. So we were looking at about 1,440 pixels for each rotation. This is a figure from one of Bryn's papers. It shows the lower part of the optical televiewer probe. You can see a centralizer there that is intended to keep the televiewer as central in the borehole as possible. And then in the lower part, highlighted by the black box, is the camera itself. And it takes images around the borehole, so it's not a down viewing camera. And this is just an example of one of the logs that we took. So this is 2 logs from the site 3 borehole. They're 150 meters in length. On the left, we've got the down log, the down direction log, and on the right, the up direction log. They look different because we use different illumination properties for these 2 logs, so the brightness varies. We're trying to get 2 different types of results out of these images: structural analysis that is ongoing, and the glacial debris analysis, which I'll present today. So glacial debris was something we really wanted to get a handle on, if we could, from the borehole measurements. As Bryn said, we didn't really know going into the field what we were going to find at all. We had no idea if the glacier was chock-a-block with debris or if there wasn't much at all. And all we knew from the drilling process was how eroded the drilling components were, and how often we had to stop drilling because we hit debris. And these panels show some examples. So the 2 panels on the left, A and B, are sections of the televiewer logs. Panel A is showing what we think is fine sediment in highly concentrated layers. And we think this is most similar to the image on the top right, which is a highly concentrated layer of fine debris, perhaps dust, seen through a crevasse in a glacier in Svalbard. As well as the fine sediment, we also saw class the varying sizes, and these are demonstrated in panel B. So we've got really tiny ones, bright reflections. All the sort of reddy gold coloured reflections are debris. And in the centre of the image of panel B, there's quite a large clast. And some of these, as Bryn said earlier, were actually protruding out the borehole wall. And I've just put in the bottom right that image that Bryn showed earlier of a debris clast protruding out the borehole wall. And some of these, with the high resolution of the televiewer, we could actually see details on the surface of these debris clasts. So actually getting the glacial debris concentrations was a mission in itself. Involved several steps, and the first one was simply to categorize the boreholes based on how much debris we thought was in there. We decided 4 categories were appropriate to describe the varying amount of debris through all 4 of the logs we had. So we had a Televiewer log from each of the 4 sites that Bryn mentioned earlier. And we very creatively named these low, medium, high, and very high debris content. And this figure on the right gives an example of some of those classifications. So panel A is showing 1 class and not much else in a section of the Site 2 log, and that's categorized as low. And you'll see on some of the other panels that different depths are categorized as different categories based on the amount of debris that they've got. Once we'd categorized each of the borehole image logs with depth, we then needed to know the debris concentration of each of those categories. And for the medium and the high classes, this involved manual delineation of all the debris we could see in some representative samples of each of those categories. And then based on the area of the debris and the area of that sample, we could calculate the debris content of those categories. For the low and the very high categories, this was quite a bit more difficult, mainly because the amount of fine sediment in those image logs. So we assigned values to these categories based on the visual similarity with other values that have been reported in the literature. And then we combined the borehole categorizations and the concentrations of each of these categories to get the mean and glacial debris content of each borehole. And with the manual methods involved, unfortunately, we couldn't use an automatic classification. There was some uncertainty involved, and we, in the paper, prescribed perhaps quite a generous uncertainty of plus or minus 50% on these categories and concentrations. So the results then of this, this is just a table of the mean borehole and glacial debris concentration by site as a percentage by volume. So we've got 6.4% by volume at site 1, it's the highest concentration. Lower concentrations at sites 2 and 4 in the mid-ablation area, and 0.7% by volume in the upper ablation area. Figures there just to remind us where those sites are on the glacier. And I just want to put those in context of what we could find in the literature. As I said, measurements, particularly at depth of englacial debris, were quite scarce. So these values are high compared to previous measurements of englacial debris, which tend to be less than 1%, even down to fractions of a percent. They were also, as we might expect, quite low compared to measurements of basal debris concentration. So we're sitting somewhere in the middle, higher than englacial debris content, and not quite at the extreme of basal debris content. What we did find, thankfully, was that our debris content was quite similar to what Anne had found from her modelling, and the model predicted that in the upper 145 metres of the ice column, just below the base of the icefall, so that's maybe within 1 kilometre of our site 3, the debris content would be 0.6% by volume, which, as I said, thankfully is quite similar to our 0.7% by volume. Now, just very quickly talk about one of the really interesting parts of these results, which is that we tried to also to look at the pattern with depth of the englacial debris content. And the panel on the right here is another example from site 3, one of our longer logs. And the black dots show the averaged englacial content for every metre. And hopefully you can see that the content increases with depth. The blue line at the bottom indicates the base of the borehole, and I'll come back to the red line in a second. So 2 main points, as I said, the borehole englacial debris concentration increases with depth, but it's also quite variable throughout. Now that red line, we wanted to take this analysis a little bit further. So we tried to calculate the equivalent cumulative debris thickness. So if we were to just take the borehole ice column and to melt that out, ignoring any other glacier processes, how much debris would be left at the surface? What we did take into account was a bulk porosity of 0.33 to account for air spaces in the debris layer once it's melted out of the ice. And that value of 0.33 was measured on Nazumpa Glacier, which is in the neighbouring valley to Khumbu. And from the red line then on this plot, hopefully you can see in the first 100 metres, there's very little change in the thickness of that equivalent debris layer. But once we start switching to higher debris contents at depth, that layer rapidly increases. I'd also like to highlight Site 1 in this analysis, because Site 1, this was the only site that we saw those very high category concentrations. This is panel A that I showed earlier in the centre with, and this is the high debris concentration that we had. And we think these are basal shears based on the fact that they have very fine sediment and they're very high angle, and that can be shown from the structural analysis that is ongoing. But because of these very high frequency layers, the debris content of Site 1 was much higher than the other sites. And we saw these basal shears, which we think are due to thrusting, only in the Optical Televiewer log for Site 1. And there was a greater presence of these layers with depth. Although we didn't see such layers in any of the other borehole images, we did see some basal ice on the surface at Site 2. So that might suggest that this process isn't just restricted to the absolute terminus of Khumbu. Just to round up then, these are the results as we saw earlier, the mean and glacial debris concentration percentage by volume per site in the first two columns. And then, as I said for that red line in the previous graph, based on the OpTV log length and the debris concentration, we could estimate both the debris layer thickness from the borehole ice depth in the fourth column, but also from the full estimated ice thickness based on Anne's modelling in that far column. And that suggests that there's 4.4 metres thick of debris at Site 1, and I think most interestingly 3.5 metres at Site 3. And just to put that into context, the debris layer varies in thickness across the glacier surface from thickest at the terminus to thinner up glacier. But even where the debris is thick at the terminus, these two images show two sites around our Site 1, tens of metres apart, spatial distance. And we've got a couple of tens of centimetres thickness in the image on the left and up to 5 metres on the right. So I think these results have been most interesting, perhaps at Site 3 where the debris layer is thinner, and as this end glacial debris melts out, it's going to add to the superglacial debris layer and affect future ablation rates that hopefully can be fed into modelling attempts. With that, I will pass on to Anne.
Thanks, Katie. So I'm Anne Rowan, I'm at Sheffield, and I'm going to talk about the modelling section of Everdrill, but just briefly, because it's very much still in progress. We were trying to move on from where we were before we started this project, making a dynamic model of a debris-covered glacier that predicted fairly low rates of mass loss that didn't match up with observations, to try and better understand the mass balance and dynamic behaviour and how to represent that in a model that could then project glacier change. So yeah, actually, next slide, please. But I will talk about both those components briefly. Have I got someone to change my slide? Yes, brilliant. With the caveat that this doesn't yet link to all this beautiful data that Katie presented, partly because I had 2 periods of maternity leave during this project, which somewhat slowed my progress, but also because it's difficult modelling, representing these complex debris-covered glaciers and their dynamics in a numerical model. So it's slow progress, but there's going to be more to come, hopefully. So the first part of the modelling developed alongside Everdrill was trying to improve a higher order model that coupled debris transport with ice flow and mass balance to better represent the high rates of mass loss that appear to be occurring in the upper parts of the ablation area of Khumbu Glacier. So this figure in the middle shows a long profile plot with distance up glacier from the terminus, and the brown bars show the amount of surface lowering over that distance along the glacier. And the key thing to see is that the ice cliffs, the density of ice cliffs and superglacial ponds to some extent correlates in the lower part of the tongue with increasing surface lowering, but doesn't seem to explain the whole story. So it's in the left-hand side of the plot. It seems to correlate quite nicely as you move up into the upper part of the glacier, which is shown on the right-hand side of the plot in the right-hand photo. That's the area where surface lowering is reaching a maximum in the upper ablation area. It isn't necessarily explained by what is called the debris cover anomaly, Well, it is, okay. So it is the debris cover anomaly, but it's not totally explained by the presence of ice cliffs and superglacial ponds that we know are ablation hotspots. But nevertheless, it's time to try and represent that process in a model to see how much it improves simulation. So if I could have my next slide, please. Thank you. The figure on the right shows DEMs of difference, a result of surface change across Khumbu Glacier from 1984 to 2015, and highlighting that the most surface elevation change is occurring in the upper ablation area. So that's what we wanted to try and represent in the model. And to do this, we took the higher order model that we used initially. We're assuming the debris was a sort of homogeneous layer with a variable thickness, but without any sort of differential ablation effects beyond that. And we thought about how to impose the sort of differences in ablation you actually see on the surface of the glacier, where, as you've seen from the photos earlier in the talk, you have ice cliffs superimposed against really thick areas of debris within, on scales of tens of meters. And to do that, rather than put that level of detail about the debris layer into the model, we came up with the equations on the right. So these are different ways of defining a parameter H0 based on randomly sampling debris distributions with different forms. And the histograms on the left show you the positively skewed uniform normal, negatively skewed possible distributions of debris within a particular cell of the model, which represents an area of the glacier surface, and how that then fits to a H0 value that we can then feed into the model to give the curve that represent in the right hand plot that shows the relationship between debris thickness and sub-debris ablation, so the melt reduction factor. And that's compared in that plot with some results from the literature, just looking at sub-debris melt rates, measurements from stakes and compared to clean ice rates. And we decided that assuming a positively skewed debris thickness distribution was a good way to represent differential ablation, the amount of differential ablation that seems to be occurring on Khumbu Glacier, and that fits with work particularly by Lindsay Nicholson looking at how much the shape of the distribution of superglacial debris on glaciers in this region. So if we then put that into the model, next slide please. I've just shown the figure on the left again because it's got that the red line in the subplot which shows where these profiles were taken. So this is model output showing the difference on the left between assuming the debris layer is continuous and on the right assuming it's discontinuous and has this differential ablation effect where we parameterize the mass sub-debris mass balance differently. And the differences, there's some differences, it's not huge. Slightly disappointingly, it doesn't account for all the mass loss that we observed. So in the lower two plots on each side, you see the black line is it's a measured surface lowering from that DEM of difference shown in the figure on the left by the red color scale, and that's along that long profile for two different time intervals. And the colored lines show the model output using different H0 values, and in each case the model is representing most, but some but not all of the observed mass loss. So it seems differential ablation is probably more important in that there's more mass loss in the right part of the glacier is represented by including differential ablation in the model which is the right hand plot compared to assuming a continuous debris layer, but it isn't explaining the whole story of why this part of Khumbu Glacier is losing mass so quickly and why that rate of mass loss is accelerating. So we then had a quick this is in the same paper had a look at a dynamic behavior that might be affecting glacier change over this time scale. So which is on the next slide, please, Katie. Thank you. So rather than trying to build a simulation of the entire Khumbu Glacier all the way down to those little ice age terminal moraines, to instead think more about whether there's a dynamic detachment and whether the upper part of the glacier, where the velocities are much higher, is actually still dynamically attached to the lower part, this very debris covered tongue. And based on limited evidence apart from the velocity observations from surface displacements, there's also this lovely photo that Katie took of a potentially basal ice close to drilling site 2, which is about in the middle of the ablation area. And so then rebuilt the model just looking at the upper section of the glacier and assuming that it had detached from the lower part, from the stagnant tongue, and that the stagnant tongue is not behaving as part of the same glacier. And so this figure, these plots on the right, show the same model results, but assuming that detachment has already taken place. And you can see that hopefully that in the lower two, the amount of observed surface lowering is better reproduced by the model in that case, particularly for the shorter, more recent time scale, implying that this detachment may have had a fairly recent effect. And the model outputs on the right show what the ice thickness would look like then in each situation. And the difference between G and H is assuming that the glacier is working as one system, and in G and in H, it's separating that into an upper active glacier. And so that's what is represented in these simulations. And it seems that that gives a better fit in terms of both the observed velocities and observed surface lowering. So it may be that dynamic detachment has already taken place for Khumbu. So if we go to the next slide, so we've identified that as one of the tipping points that potentially accelerates glacier mass loss, because once it detaches from its tongue dynamically, the upper part of the glacier is actually much smaller than it appears. And so there's a physical loss of mass and all in one go, potentially, as long as that detachment takes place. But there's also then moving further along the sort of evolution of this glacier. Khumbu is heading, based on the model, running the model forward in time, towards a physical detachment where there's actually exposed bedrock between the debris-covered tongue and the upper active section of the glacier. And that's, we expect to happen further up ice than the dynamic detachment. So you can see in the top left model outputs that will occur somewhere near the base of the ice fall, most likely. And at that point, the debris-covered tongue has no input of mass, even if it does at the moment, and it will either melt very quickly or turn into a rock glacier of some sort. So the active section of Khumbu Glacier will just be the upper, from the base of the icefall upwards into the western Khum. And this has already happened for other glaciers in similar areas of the Himalaya. So Logistical Glacier, which is actually in the same valley. In the photo on the right, you can see that the debris-covered tongue is completely detached from the active glacier, which has then receded far up the valley, and there's bedrock exposed between them. So they then, building a simulation of the whole glacier for Khumbu may not be a particularly accurate way of representing its dynamics, because the tongue, at some point in the future will detach, but is probably actually not functioning as part of the same glacier even now, because there isn't this bedrock exposed, but there is a difference in dynamic behavior and some evidence for detachment. So there's more work to be done looking at how to develop the modelling using the data we've collected, which I need to get on with, particularly constraining the model against the borehole temperature measurements and the distributions of debris that we've seen from the Televiewer logs. But I will hand over to Duncan.
Thank you, Anne. And so I'm slightly mindful of time, but just briefly to cover a few ideas that we've got for our next steps. If you could just advance the slides there, Bryn. I think as a group, we consider perhaps the end glacial temperatures to be perhaps the most interesting finding to come from the project. And that's something that we want to explore in a little bit more depth, no pun intended. And particularly thinking about where the additional heat comes into the system that perhaps accounts for the raised ice temperatures in comparison to mean annual air temperatures that Katie talked about. So if we assume that the ice is to form at the temperatures that it falls at in the Western Khum, then we might consider the firn layer to be forming at a temperature of around -9 degrees at best. And there's data from the north side of the divide again that bears that out to suggest that the ice is starting to form at that sort of temperature, initially at least. So there's quite a gradient for the ice to go through in terms of temperature increase as it flows through the icefall and down into the ablation area where we recorded it. Next slide, Bryn. So thinking about what some of those controls might be is one area that we're really keen to focus on going forward. And some ideas that we've got for that are potential control of the geothermal heat flux. And there's been a little bit of work again on the East Rongbuk Glacier on the northern side, which concluded via a modelling exercise that actually the glaciers on the northern side respond to changes in air temperature much more than they do to any change in geothermal heat flux. And there's the DOI that you can follow up on the right-hand side for more information there. we wonder if there's potential for englacial heat through the frictional effects of fast flow through the icefall. Recent work's shown that the ice going through there flows at about 300 or 400 meters a year, which is pretty impressive for a glacier in the Himalaya, but only for a length of about 1 kilometer. So we suspect that that may not be such a significant control. Potentially there's a role to play for the hydrology in the ablation area and also the ponds and the cliffs that Anne has already slightly alluded to, but mainly the processes that they would bring into the system would take place at areas below where we actually measured our minus 3.3 degrees. And so really I think we're going to exclude those as being some of the major controls, at least on the temperatures that we were able to measure. Next slide, Bryn. So then the last hypothesis is to do with melt and sublimation, and some of Tom Matthews' work, which has been in the upper accumulation area and putting in temperature, well, in fact, automatic weather stations to measure all parameters all the way up to the South Col, has already suggested that the latent heat release from refreezed and meltwater could be a possible factor to consider in warming the snow before it even transitions into the glacier ice. And recently published data anyway from Takuchi et al. Also suggests that that process could be significant at the higher elevations. So I think one thing that we'll be really keen to do, it will be quite ambitious, is to get up above the icefall and really start to take some measurements within the firn and within that upper accumulation area to see if the melt and refreezing of meltwater can account for some of the warming that we see through that relatively short section of the glacier. Okay, so I think that's our last one. If you advance, Bryn, we'll just leave it there in terms of the presentation and perhaps, well, leave a short time for Tavi to introduce next week's seminar.
Thank you very much indeed, Duncan. Yes, just to say that next week's seminar, Tolly, Christina Aldergersdottir, and all the glaciologists in Iceland, so that will be quite a choreography if they all appear on screen, to talk to us about the glaciers in Iceland during the last and current century. But thank you very much for a fantastic talk to all four of you. The way that we usually do this is questions is to ask people to indicate on the chat if they have a question, and then we can pass it to whoever it seems most appropriate. Paco has a question for Anne, apparently. Do you want to unmute yourself, Paco?
Yes. Can you listen to me?
We can hear you, yes.
Okay, thanks. So it was really nice talk. I really enjoyed both the science and also the logistics. It's surprising how all of these things, for instance, the loss of power of the motors because of lack of oxygen, or even the maximum load of helicopters. So there are simple things, but if you are not into it, then you do not think about it. So it was really nice. I have a couple of questions to Anne regarding the modeling. And in particular, so you mentioned that you were using high order modeling. Maybe you use Elmer or maybe something else. But I'm worried about the constitutive relationship because you didn't mention, or I didn't understand, or I didn't catch it. Did you use a regular constitutive relationship, so Glenn flow law? But because in this particular case, having that much amount of debris inside the glacier ice, then probably the constitutive relationship could be quite different. And then maybe you are, if you are using a regular one, then maybe you are predicting things which are different from reality.
Yeah, so that's a good question. So the model we used is David Eggham's isoscia model. So it's higher order in that it sits between a shallow ice and the Stokes model. So it's not as sophisticated as Elmer, but it's got the the important stresses for a high relief glacier flowing through mountainous terrain. In terms of the composition of the ice, it's a case of parameterizing viscosity, I guess, which is something we don't have. Well, now we do, I guess. So but we don't have information about how the composition of the ice then relates to its viscosity. And that would be a nice experiment to do. You know, we could do that in a laboratory experiment and start to parameterize that better. To get round that as one of many sources of uncertainty in the model, and what we tried to do was constrain it by observations. So the model's actually spun up with relatively little information about the glacier itself, and then it's tested against a longer term Holocene evolution from the marine record, but also, you know, the velocity data they showed, and things like this, trying to constrain the surface lowering to see if we're getting the dynamics about right. But you know, no model is completely accurate, sadly.
Okay. And then you also mentioned that you have observed this temperate layer, basal, lowermost. And did you take that into account for the modeling?
Not in this modeling. So it is a model that considers ice temperature, but we didn't constrain it with those observations. So that's the next step. And I think actually something like Elmer ice would be a good way to do that, because it more explicitly considers the thermomechanics. So there's a really nice paper by Adrian Gilbert doing this for another Rikasamba Glacier in the Nepal Himalaya. And I think we could take a similar approach at Khumbu. Now we have the data to constrain that from the boreholes. But that's work in progress, or needs to be in progress. I'll get back to you on it.
Okay, thank you.
Are there any other questions? I'm aware that some people may have had to slip off because we've hit the hour. I guess this is one of the routes up Everest. Is that right? Does this have any implications for people who wish to go and climb Everest?
Yeah, certainly it does, Tavy. I mean, the area that we were working at the top is very close to Everest Base Camp. It's increasingly dynamic, perhaps not in terms of the ice flow, but in terms of the movements around and about. It's becoming increasingly unstable, and through the ice fall, as the ice warms, as Katie has suggested, over that few decades for which we have the measurements, if that ice warms, then it becomes increasingly unstable, and that's exactly the zone that is already extremely hazardous. So I think it does have real implications for people who are climbing. Yeah.
Are there any other questions for this group? Okay, well, thank you very much indeed for your presentation. And thanks so much for the choreography of 4 people presenting. That's a real professional handovers and slide control. So thank you very much indeed. We really appreciate it. And yeah, hope to see everyone next week.
Thanks a lot.
Thanks. Bye.
Katie, I hope you get your computer sorted.